All right, guys, we're going to go ahead and start talking about Chapter 8, looking at chemical equations and chemical reactions. Now, a chemical reaction we talked about at the beginning of the year, we said that a chemical reaction, what it does and what's different than a physical, is that when a substance has a chemical reaction, it changes that identity. It changes into something completely different, something new, okay, something that's very hard to reverse. Now, in a chemical reaction, we will have reactants and we will have products. And the reactants are always going to be what we start with. They're the original. And the products are going to be the result of the chemical reaction. It's what's being produced. Another way to remember this, in a chemical equation, we look and we see, and the arrow will always point towards the product. Okay? Now, one concept that we've talked about for a while in class is the law of conservation of mass. Remember that the law of conservation of mass basically states that the total mass of the reactant is going to equal the total mass of the product. What we start with is what we finish with. We don't create mass or destroy mass, it's just transferred. Now, in the chemical reaction, what we see is we have a couple examples here. Here we have a visual example. Here we have the actual chemical equation written out right there. And then below it, we're representing with the masses. Okay, so here we see that we have two magnesiums reacting with an oxygen molecule to produce magnesium oxide. Here we see that example written out for us. We have two magnesiums, one oxygen molecule reacting with and making two magnesium oxides. Now here we look and we see that we have the masses as well. And we see that the total mass of the magnesium is 48.6 grams. The total mass of the oxygen is 32 grams, which gives us a product of 80.6 grams. Okay, a chemical equation, what it does is it represents the identities and the relative amounts of reactants and products in the chemical reaction. The identities are going to be the actual symbols from the periodic table, like magnesium or oxygen, or in this case we have magnesium oxide. And then the relative amounts will represent by the coefficients in the front of the formulas. Okay, so it tells us what we're dealing with and how much of each thing we have. Okay, it uses the formulas and the symbols. Now, so we have a little example question. It says if 35 grams of chlorine reacts with 39 grams of potassium, what would be the mass of the product, potassium chloride? Well, here we have 35 and 39. We know that the sum of the reactants are going to equal the product. So we have 35 plus 39 gives us a total of 74 grams of potassium chloride. Whatever we start with is what we're going to finish with. Now, things we can look for to see if a chemical reaction has taken place. Okay, some key things that we see. We can see heat or light. We really can't see heat, but we can definitely see light. We can see gas bubbles, like in this picture over here. We can see a precipitate. A precipitate happens when a solid falls out of solution, meaning that the solid is insoluble in the water, and so therefore it falls out, and basically it's a clumpy stuff at the bottom of a beaker, or in our case, in the bottom of a mini well plate. Okay, and obviously color change is very easy to spot. We can see an example of it down here, going from very clear to bright yellow. Now, when we are writing elements, because in a chemical reaction we're going to have to write elements and we're going to have to write compounds. Most pure elements are written as just the element symbol, but we have diatomic molecules and we have some other exceptions. So let's start here first, meaning the pure elements. So just their symbols, that would be an example of that would just be like from before, magnesium, or just writing calcium, or just writing our phosphorus. Okay, it's just the element. Now, the exceptions to this, so anytime we see an element, we always have to think of the exceptions before we write it, are the diatomic molecules. Now, what diatomic means, it means two atoms in the molecule. And here we see that we're going to break those up into Brinkelhoff. And these are the guys that we use. bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So anytime we write these guys by themselves, we'll write them, and this is just by themselves. Remember, when they're in a compound, we usually have to do either crisscross if it's ionic, or we use the Greek prefix system if it's covalent. But we look, when it's by itself, we always give it a 2. So H2O2, N2, F2, Cl2, Br2, I2. Okay. Some other exceptions that we have are sulfur. Sulfur by itself is written S8, and phosphorus is written P4. These guys really aren't too terribly important for what we're doing. Just know that there are some other exceptions out there. Now, so we have our elements and we write them, and we know how to write our formulas from chapter 7. So usually what we do to take a equation from a description into a chemical equation, we usually start by writing a word equation. And what a word equation is basically what it sounds like. We use the names instead of the formulas, and it kind of helps break it up from just a paragraph of a reaction into a word equation, and then finally into our chemical formula. Okay, some things that we need to know inside a chemical equation. We see that the first off, we have our arrows. This arrow indicates that the chemical reactions happen. It means to yield, to produce, to form. But basically what the first arrow means, it's just the chemical reactions happen. Now the second arrow means it's reversible, meaning that we can go forwards and backwards in that reaction. So the reactants can become the products, and then the products can reverse it back around and go back to what they originally were. Some other things we can see, anything written above the arrow. Okay, so we're talking about these arrows up here. So anything written above those guys, if we see the triangle or heat written above it, that means that heat is needed in the reaction. If we have a symbol above it, that means that a catalyst is being used. Remember, a catalyst just speeds up a reaction. It makes it go faster. It's not involved in the reaction, but it just makes the reaction go fast. Okay, so if a symbol's above the arrow, then that's a catalyst being used. If we have a temperature, that means it's a specific temperature required to have the reaction take place. And if we have a pressure, like on the very bottom here with 2 atmospheres, then we know that there's a specific pressure required. If anything written after the formula, so we're looking at each individual formula, if we see that it has a solid in parentheses, that means that it's a solid. L is a liquid. AQ is aqueous, meaning dissolved in water. And G is a gas. Okay, and that is just after the equation. Now let's go ahead and work some examples. Our first description that we have, it says solid sodium oxide is added to water at room temperature and forms sodium hydroxide. So the main thing here that we got to pick out from the description, we have sodium oxide is added to water at room temperature, and it forms, there's our arrow, and we have sodium hydroxide. So we can go ahead and take this guy and write it in a word equation. So we have our solid sodium oxide plus our water, and then we have our sodium hydroxide as a product. And then we take this guy and we're going to go ahead and take it to the chemical equation. We got to write the formulas here. So first thing we have to do is we have to use our naming skills to write the formulas. And here we have sodium oxide, which that's going to be an ionic compound because it's sodium. So we have Na, which is a +1 oxidation number. Oxygen, which is a -2 oxidation number. We crisscross these guys and we get NaO, Na2O. And it reacts with water. I hope everybody knows that water is H2O. And then it forms a product of sodium hydroxide, which again, that's an ionic compound. We have sodium, which is +1. Hydroxide, which is a polyatomic, is OH with a -1 charge. We crisscross these guys and we see that we'll get a product of NaOH. Okay, and this written all nice and neat for us without the crisscrossing up there. Look like this. Here's our formula equation. And guys, realize that this equation is not balanced. Okay, moving on to another example. Here we see that we have the description of it. We have solid zinc 2 sulfide. So we know that we have that. It's reacting with, we see a plus sign, oxygen gas. And it forms solid zinc 2 oxide and sulfur dioxide gas. So we got a couple things going on here. First of all, let's take it into our word equation. We have the zinc 2 sulfide is solid with the oxygen gas, and it should be solid zinc 2 oxide, should be an S there, plus sulfur dioxide and a gas. So now we got to take these guys and write the formulas for them. It tells us that it's zinc 2 sulfide, so that 2 tells us that zinc is a +2 oxidation number, sulfur is going to be a -2. We crisscross these guys and get Zn2S2, which we reduce down to ZnS. Reason why we crisscross there is ionic. The zinc 2 sulfide is ionic. And then we have our oxygen gas, which our oxygen gas is just oxygen by itself. But remember, anytime we write an element, we got to check, is it a part of Brinkelhoff? Is it a diatomic molecule? And yes, oxygen is, so we put O2. And guys, that's going to become really important when we get into balancing. And then we have zinc 2 oxide. So again, it's an ionic compound, so we got to crisscross. So we have zinc, which is +2. We get that from the Roman numeral. Oxygen, which is -2. Crisscross those guys, and we get Zn2O2, which reduces down to ZnO. And it says we have sulfur dioxide gas. And this is nice because it's a covalent compound. It tells us what to put because of the prefixes, so it's just SO2. And guys, obviously we would bring down the solid, we would bring down the gas, we would bring down the solid, and then we would bring down the gas. Okay, and that would be our equation. And obviously, guys, written nice and neat. I'll let you look at it. This is not balanced.